go ahead and do our very last topic, which is a nice little smorgasbord, a cornucopia of mathematics, a piñata of excitement. And it covers sequences, series, mathematical induction, which is absolutely neither here nor there, and statistics. So it's a modest sampling of different math. Very different types of math as well, but we're going to look through it here. And I think you've at least seen bits of this here. Induction you probably didn't see unless you had a really cool geometry course where you proved things inductively. It's one of the coolest ways to prove something that there is. It's absolutely gorgeous. And then this is the most basic stats that you could possibly do. And we're going to be mainly doing it with calculator techniques. Same thing with series. So it shouldn't be too much new material today. Let's get down to it. So sequences. That's not auspicious. There we go.
I totally know what auspicious is.
Awesome. So sequences is just a list of numbers that has a pattern. So, for instance, we usually say little a sub n as a way of denoting a sequence. And you can say, like, here's one which is tough to... Ooh, where'd that come from? 11. So, take a while.
I'm not going to figure this one out.
It's sort of some Da Vinci level code stuff we've got going on here, but the particularly clever will have noticed that we're adding 2 each time, and that's the pattern. We can have all sorts of different patterns to numbers. We're going to be primarily concerned with arithmetic sequences and geometric sequences today. But you can have other patterns. So, for example, here's a favorite one. Right, this is not arithmetic. I'm not adding the same thing every time. I'm adding 3, I'm adding 5, I'm adding 7, I'm adding 9, I'm adding 11. I'm not multiplying by the same thing. To get from 1 to 4, I need to multiply by 4. To get from 4 to 9, I'd have to multiply by not 4. Right? So it's not arithmetic or geometric, but there's a definite pattern if you look, and that is, yeah, there's squares. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So it's just all the squares marching on up. This is a particularly beloved example by people who like crafting that sort of next level of pattern, because they like screwing around with the squares of the first 6 numbers or so. If they want to be really sneaky, they'll do like 0, 3, 8, 15, 24, 35, where it's all just 1 less than all the squares. So, I know. So 2 bits of vocabulary. So we'll say that a sequence is explicitly defined if it's an equals n stuff. So for example, an equals 3n plus 1, or an equals n squared plus 7n, or something like that. What an explicit sequence definition gives you is, if I want the 5th term, I just plug in 5 everywhere I see n, and it gives me what the 5th term is. I just plug in 5. And it's that simple. So the 5th term of this top sequence is just 3 times 5 plus 1. It's just 16. So explicitly defined sequences are great. We can find the 400th term right away. I just plug in 400, and that's where my 400th term is. As against an explicitly defined sequence, there are recursively defined sequences. So any of you who did like computer science type stuff had to deal with maybe programming recursively from time to time. And recursive is, humans hate doing recursive things. Computers, however, are cool with it. So, whereas in an explicit statement, I'm just going to see numbers and n. In a recursive statement, I'll see an equals, and I'll see like an minus 1, an minus 2, an minus 3. What those mean is that to get this term, I've got to know the previous terms. Right? So I can't get a 300 until I know a 299. I can't get the 500th term in the sequence until I know the 499th term. And I can't get the 499th until I know the 498th. So everything is defined recursively in terms of the earlier stuff in the sequence. So the gold standard of these is, of course, the Fibonacci sequence, where you have to start with a couple of starter terms, and then you define the next term as the sum of the previous two. So if I have 1, 1, A3 is going to be A2 plus A1. The third term is going to be the second term plus the first term. 2. My fourth term will be my third term plus my second term. 2 plus 1 is often 3. My fifth term will be my fourth term plus my third term. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. And so on and so on and so on. So notice, this isn't explicitly defined. I can't just hop straight to this guy. Because to know this guy, I've got to know those two first. So recursive sequences, you've got to start at the beginning and work your way forward. There are some recursive sequences where you can figure out an explicit pattern easily and treat it explicitly. Other ones where it's really rather tricky. So sometimes it's just easier to let your computer chug its way through and find the answers for you. So that's the only difference between the two. And they're easy to tell which one you're dealing with. If it's n's and numbers, you're here. If you see little a's popping up on the right side of the equal sign, you know that you're recursively defined. And that's a recursive type sequence. Now, here's where the magic happens. So, arithmetic and geometric sequences. So these are particular types of sequences for which the mathematical manipulation is relatively pleasant. Arithmetic sequences are ones where, to get from one term to the next, you just keep adding the same number. So these are from term to term. Just add the, what we call common difference. So I'm just adding the same thing each time. This is an arithmetic sequence. I'm just adding 2 each time. A geometric sequence is where I'm just multiplying by the same thing each time, and instead of calling it the common difference, we call it the common ratio. Note the difference. There's going to be a question on either the speedback or the final itself related to just knowing these terms, where they'll say, here's a geometric sequence, what's the common difference? And it'll be up to you to remember, like, oh, wait a minute, common difference is an arithmetic sequence thing, not a geometric sequence thing, you silly test. And then you'll have to correct it accordingly. So the good news is that these guys are pretty standard to deal with. And it's easy to recognize which is which. Right? So, I didn't want to do that. What I wanted to do was this. Right? So it's clearly not arithmetic. So chances are it's geometric, but if you really wanted to be sure, just divide these numbers. See if it's the same thing when I divide those numbers. Yay! And what I get when I divide the second term by the first term is the common ratio. So I already know that it's geometric and that r equals 4. To get the common ratio for a geometric sequence, just divide those two terms by each other. And you're there, you're done. Right? It's no more difficult than that. There are people who do lots of weird things to try and get the geometric, the common ratio for a geometric sequence. Just take A2, divide by A1, and you're there. Technically, if you wanted to be an outstanding human being, you would make sure that 192 divided by 48 is also 4, because they could be absolute dicks about it and give you that's 4, and this is like 3.9 or something, just to screw with you. Then you'd say like, oh, it's not actually a geometric sequence, you sly boots. But you, if they're at all decent people, they wouldn't do that to you. But that's not saying much. So how we're going to deal with this is we have some nice formulas, which I'm going to give to you now. So here's your arithmetic versus geometric. Here is your general equation, and here is what to do if you're given two random terms. So the general equation for an arithmetic sequence is the nth term is just the first term plus d times n minus 1. Makes sense. If I want to go from turn 1 to turn 50, I just need to take 49 steps of whatever distance each step is. Right? Just, if you think about it physically, it makes sense. Just think of yourself on a little number line in a jaunty little number line hat, and you want to get from term 3 to term 7. I got to take 4 steps, and each step is going to be that length. So you just take those 4 steps, and that gets you where you need to go. For a geometric sequence, it's the same type of horse. I'm going to start at my first term, A1, and then I'm going to multiply by my common ratio, n minus 1 times. Right, so keep in mind it's always n minus 1, because if I'm at step 1 and I want to go to step 4, I need to take 3 steps, right? Not 4 steps. I need to take 3. So for an arithmetic sequence, those steps are just multiplying. But for a geometric sequence, because it's all about, we're multiplying by a common ratio, it's all about raising to powers. So I'm going 7 times 7 times 7, or 7 to the third, instead of 7 plus 7 plus 7, which is 3 times 7. So let's get comfy in those, and then we'll use our super secret awesome ones, which I thought were actually relatively common knowledge, until I started getting reports from students who brought these to their teachers, and the teachers were like, wow, that makes things easier. And that was dispiriting. But what can you do? So we'll do these first. So if I have, for instance, this sequence, let's say 3, -1, -5, -9, and I want to write the general equation. And I want to find term 30. So you could see the pattern and then write out 30 terms. This is not an uncommon thing for students to do on SATs and such, but we're awesomer than that. So let's do it legit like. So what is the pattern? Is this arithmetic or geometric?
Arithmetic.
It's way arithmetic, right? I'm just subtracting 4 each time. Okay, so my D, I know it's arithmetic, so I know I'm here. I know my D is -4, so I'm just subtracting 4 each time. And I know my first term is 3. Therefore, hence, and furthermore, I can write down my general equation. I just plug in the numbers. Plug in my A1, plug in my D. There are some people who just can't stand having this n-1, who will then distribute for their own twisted psychological reasons. If you're one of those people, the angels are weeping for you, but you can do it. If you have that particular mathematical fetish, that's fine. But this is also totally acceptable. Your choice. But this is the general equation. And then from there I can figure out any term that I want, right? This is a nice explicit equation. It says an equals n stuff. So I can figure out any term I want relatively easily. So if I want to know the 30th term, I should have said 31st term. I can do that. So 29 times -4. -116, don't trust me.
Yep.
Okay.
Okay.
A minus 116, so -113. So if you wrote this sequence out to the 30th place, you get -113 out of it. So that's kind of neat little power to have. Likewise, if I have this scintillating little sequence of numbers, geometric or arithmetic? So yeah, this is geometric. My ratio is what? What am I multiplying by each time? 1/2. My first term is the term that's first, is 8. And so we're just going to plug that junk into here. That'll give me my general equation. My general equation is my gateway to every other term in the universe. So an is a1 times my ratio to the n-1. So let's say I want to find, I'm not going to find term 30, that's going to be ridiculous. I want to find term 10. So that'll be 8 times 1/2 to the 10th, which is going to be a small number. But give it a try.
Shouldn't it be to the 9?
Oh, it's the 9th. Yeah, thank you. I mean, I was testing. So 1/2 to the 9th, of course, which is, we all know, is 0.01565. Times 8.
Oh, no.
Is that with the times 8?
That was with the times 8.
All right.
Change it to a fraction.
0.015625. Is that the end of it?
I think so.
Okay, fair enough. Could be. So yeah, that's great. When they give you the sequence, life is pretty good. But if they, instead of giving you the nice first 5 terms of the sequence, what if they tell you, hey guys, this is an arithmetic sequence, the 4th term is 52, the 7th term is 98. What do you do then? Well, find the middle. Just keep taking the middle. Well, luckily, just use common sense. The common difference is going to be how far apart are those two terms. So I'm just going to subtract the values of their two terms. And then to get how big each step is, I'm going to divide the total distance by the number of steps. That tells me how big each step is, as denoted by that. So I'm just going to take an minus am and divide by n minus m. The distance that I go along the number line divided by the number of steps that I take gives me the distance per step.
And what's n?
So n and m are the two terms that I'm given. So, for example, if I got, it's an arithmetic sequence. Where's that going? There we go. It's an arithmetic sequence, and I know that my 4th term is 10, and my 12th term is 42.
Great.
And I want to know, thank you, I want to know what the common difference is so that I can write a general equation or I can find another term or something like that. I just subtract the values divided by, subtract the indices. Yeah. Indices. So the common difference is 4. So if I wanted to get A5 or A6 or A7, I could just apply 4 however many times I want. So if I want to write the general equation, now that I know D, I can just pick either of my other terms here and solve for A1. So I could say like, hey, 10 equals A1 times 1 minus 5. So A1 is -2. So the general term for this sequence is just -2 plus 4n minus 1. So once you have the common difference, just plug it and one of your points into the general equation and solve for A1, if that's what you're looking for. Okay. So that's how it works for our friend, the arithmetic sequence. The geometric sequence works quite similarly, but it looks nastier, but just keep in mind it isn't. So it's going to look intimidating, but if you feel intimidated, just know that your feelings are wrong and bad, and be ashamed of them. So we're going to take a look at this guy. So if you're given two random terms in a geometric sequence, to get the common ratio, I'm just going to divide them, and then I'll take the n minus mth root. Okay, so that looks horrible, but it's not too bad. It makes just as much sense as this. Just like this, I took the distance that I covered and I divided it by the number of steps. Here, same thing. By dividing these two powers, or by dividing these two values, I get the total amount of multiplying that happened. And then I'm just going to say, all right, how many multiplications happened to get this big number? Well, n minus m multiplications happened. If I'm going from term 3 to term 7, I multiplied 4 times, so of course I want to take the fourth root of that big number. So all this is saying is, take your total distance covered and take the root of the number of steps. Instead of dividing by the number of steps, I take the root of the number of steps. That's all she's saying. So it looks weirder than it is, but it conceptually makes some sense if you start thinking about it, kind of. I will say that in general life, these guys are sort of expected that you have some grasp on them. This is pretty rare for them to expect that. So that's how to deal with sequences. And that's really all that there is to say of sequences as far as this class, the course that you guys are taking, is concerned. There's some really quite cool things that you can do with more interesting and involved sequences, but you're not going to do it. Really, you just need to recognize an explicit versus recursive. You need to be able to, if you're given a recursive definition, be able to take it out to a certain number of terms. And you're going to need to be able to, given a list, write the general equation and find a random term, or given two random terms, to be able to write the general equation. That's what you need to know about sequence. So, let's say they tell you, I have this lovely geometric sequence. I know that the fifth term is, let's say, 4. And let's say that the eighth term is 500. Let's write, hey kids, let's write the general equation. So just like your favorite Saturday morning programs, let's do this. So I first need to figure out what my common ratio is, because they said it's geometric, so I know I'm looking for my common ratio, not my common difference.
And they'll always tell you.
Yeah, if they're going to do this sort of thing, they have to tell you, because otherwise you wouldn't have no way of knowing how I got from this term to this term.
Could you just do them both and see what...
Sure you could! That's very enterprising. The rest of us, we're just going to wait for them to tell us. So R is divide the two terms, divide those two guys, and take it to the...
Wait, 500?
Yes, 500. Don't know where that came from. 500 divided by 4, and take it to the 8 minus 5th root. So 500 over 4 should be 125. If I
Wrong answer.
to the 1/3 power. What's the cube root of 125? 5. So R is 5. And now I can plug into my general equation, 5, and then one of my points to figure out what A1 is. We'll do it here. So I know I'm going to always use the one with nicer numbers. So I know A5 is 4.
500 is a much nicer number.
And this is term 5. So 5 to the 4th is 625. Thank you. So A1 is this lovely term, 4 625ths. So my general equation would be 4 625ths, 5 to the n minus 1. Using that, I could then get any other term in the sequence, which is really quite powerful. Going from two just totally random terms, that's all I know, I can now figure out any other term in existence for this sequence. Just knowing two terms and that it's geometric. So now if you wanted the 500th term in this, you could get it. If you don't remember how to deal with these roots in your calculator, just straight up enter this as 125 hat, parentheses 1 divided by 3, and you're fine. Right, your hat is to the power, and so when you're taking fractional powers, just take hat and put that fractional power in parentheses, and you're good to go.
How else would you do it?
How else? You know what the cube root of 125 is the other way. Sometimes, if you have some calculators have a little box here that you can fill in, then you would just put a 3 in there.
Like mine.
Yeah. So there you'd have to say 125.
I don't know which root.
Either way, it's all cool. So what a series is you start with a sequence, you start with a list of numbers, and then the series is just add up the terms. So you have a sequence as your base. Then add the terms. So for instance, if this is my sequence, then my series, the first term in that series would be add the first term. The second term is what I get when I add A1 plus A2. The third term is what I get when I add the first 3 numbers.
Oh, first 3.
The fourth term is when I add the first 4 numbers, and so forth. So in general, Sn is A1 plus A2 plus A3 plus the nth term. So if I want a term of the series that comes from this sequence, that is just add together the first n terms of that sequence, and that gets you that part of the series. So it's all about adding together. Now, there are equations that go with this sort of stuff, but the easier way to do it is pretty much to come up with the general equation for the sequence and then slam it into sigma. So all of you have a sigma button on your calculator somewhere. So this is one of the nice things where we're all at the same place. Everybody's got a sigma button and it works almost the same for everybody. There's some variation between 84s. I think the plus versus the silver has some weird things going on. So for some of you, what you have to do is do it in parentheses style. And for others of you, they give you little boxes to fill in here.
No, I got the boxes. What's better, the boxes or the
For
The boxes.
That's what I'm
Mine
thinking.
just has the thing.
So, for example, well, let's take this jolly little guy. What is his general equation? So that's what I put in here. Or, if you don't have this version, you'll put the general equation in here. So what's the general equation for this sequence? It's a good exercise for you guys to do. So just what we did before. General equation. And here is where that proclivity to reduce it down actually comes in a little bit handy. So what I could say is that this is 4n minus 3. Either way. So if I wanted to add up If I wanted S40, for example, if I wanted to add up the first 40 terms, I could write out the first 40 terms and add them all together. Or I can just say calculator. This just means add up. It's a Greek S for sum. So I can say, if you've got the little fill-in things, you can say x equals 1 to 40 of 4x minus 3. And it will give you an answer. If you don't have the little fill-in-y things, you'll do like sum,
3,160.
and then
No, that's not the answer.
I'm trying to recall if for the old 84s, whether you need to put that x in there or whether it assumes that it's the only variable that's there, so it must be the variable. But I'm pretty sure this is the order if you don't have that fill-inable sigma notation there. So the thing is that sigma notation is actually much more powerful than the equations that you're given to specifically deal with series, because those equations can only add up the first n terms, 1 through 40. This way, if I wanted to add up terms 20 through 40 for some reason, I could do that. I could just say x equals 20 to 40, and it would add up terms a20 through a40. So sigma notation is very powerful, and it's not that hard to get a handle on. You just have to get comfy with making general equations. If the general equation just gets slotted right in there. If you're desperately in love with the idea of knowing the equations, they're in your packet there. I mean, it's these guys from back in the day, where you set like a1 times 1 minus r to the n over 1 minus r to the n, that stuff. For most cases, they have to ask a really around the barn type of question for this not to be way more useful in general as a tool, mathematical tool going forward. Okay, so let's try one. Let's see what you can do. It's time to see what you can do to test the limits. So here we go. Let's say this is your sequence. Let's say 3, 6, 12, 24, 48, 96, etc. So, find S22. So, what did we get?
125829009.
Yeah.
582,909. Yeah, 12,582,909 is what you should have gotten. And the setup for that was we wanted to go from term 1 to 22 of this guy. He's geometric. I'm multiplying by 2 each time. So it should have looked like that. I put in my geometric general equation. So if stuff fouled up, so on how I would enter this on my calculator is 3 times 2 to the parentheses x minus 1. So induction is another way of proving things. So you've got three ways of proving things, 2 of which you remember and 1 of which is the secret way. And once you learn this, you're sort of in the club of secret math people. So 3 ways of proving stuff. So there's the direct approach.
This is like framed downstairs.
So,
It does.
the direct approach is the one that you were used to back in geometry, like the 2-column proof, where where you have some things that you know, and you use axioms and postulates and theorems to work towards the thing that you want to prove. So you have some givens, and you go to what you want to prove using postulates, theorems, and axioms, and all that good stuff, and definitions. So that's the direct way. That's the one that you did like 95% of the time. And if you... Those are so fun. That's the best part of geometry.
That was too long.
Possibly. And then you did those a lot. Then you also learned, and you did them for like a week and then forgot about them, the indirect way of proving things, otherwise known as the proof by contradiction. Which is my favorite. Actually, this induction one's my favorite, but this one's up there. So, contradiction, remember what you did was you basically assumed the opposite of the conclusion that you wanted, and then you showed how that resulted in a paradox. So you said, well, if the opposite is not true, then what I originally wanted must be true. If not x is false, then x must be true. So you assume the opposite of the desired conclusion and show how that assumption leads to absurdity. Mathematical absurdity. And so since the opposite of the desired conclusion led to mathematical absurdity, therefore the desired conclusion must in fact be true. So you would say like, prove that for all even numbers 5 times that number is even. You would say, well, suppose it wasn't even, suppose it was odd, and then you would work through a series of logic until you discover that that resulted in an absolutely absurd mathematical statement. And so then you said, well, I guess my assumption that it was odd is wrong, so it must be even after all, and therefore I have proven by contradiction my original intended statement. It's a beautiful way of proving things. So I would recommend you, when you're doing your leisure math tonight, look into it. Look into some indirect proofs. They're really quite fun. What we're going to be dealing with is proof by induction. Which is great. When you can do one of these types of proofs, it's absolutely beautiful. Because it's such a neat trick. And what these are for is therefore proving statements about A sub n type quantities. So stuff with indices in them, stuff with little, subscripts here, where you're proving that something about the relationship between terms and indices. So for example, you might want to say that if I add up, let's say I've got you might want to say the sum of the first n terms is n times n plus 1 times 2n plus 1 divided by 6. Alright, so this is a statement which relies on indices. And so it's a candidate for proof by induction. Anytime where I have a statement asserting some equality, and that equality is based on an index which can change, I'm probably going to want to look into proof by induction. And how inductive proofs work is 2 steps. 1, prove that it's true for n equals 1. Now here's the neat part. 2, prove that if the n case, I guess you guys call it the k case. The n case is true, then the n plus 1 case must be true. Now what that does, it's really elegant in that all you do is prove that the first term is true and that whenever I have any random term true, the next one must be true as well. And what this does is it builds an infinite chain of truth, which is absolutely stunning. So if I know that 1 is true, and if I know that if a previous case is true, the next must be true, then that means that 1 being true makes 2 true. And that 2 being true makes the n equals 3 case true. And that n equals 3 being true makes the n equals 4 case true, which means that for any number from 1 to infinity is true. So I have proven this statement is true for all possible values of n, and all I did was prove that it works for n equals 1, and then prove this case. Prove that if I assume the truth of this, that this must follow. It's a lovely way of doing it. They, of course, can't, on a multiple choice test, have you actually prove anything inductively. So what they'll ask you is, here's the statement that we're trying to prove, show us what the n equals 1 case is, what the n case is, what the n plus 1 is. I think that you guys use the letter K instead of N. But same idea, you just use the letter K. So for example, let's take this guy. I'm going to try and prove that he's true, and I hope I remember that formula correctly. That if I add up the first n squares, all I have to do is take n times by n plus 1 and multiply by 2n plus 1, divide by 6, and that's the sum. So let's see that it works for n equals 1. Is it true that if I add up the first 1 terms, that's the same thing as 1 times 2 times 3 over 6? Yep, that's true. If I add up the first 1 term of this, I get that. This is also a good party trick, by the way. If you ever want to add together the first 10 squares, it's just 10 times 11 times 21 divided by 6. Kind of cool. So I've proven that it works for n equals 1. From there, I'm going to prove that if I assume this is true, that the n plus 1 case must follow as true as well. So I'm going to assume that S sub k equals k times k plus 1 times 2k plus 1 over 6. This is called the k case. I just replace all the n's with k's. Yes. So what I want to prove is that if this is true, then sk plus 1 is k plus 1 times k plus 2 times 2k plus 1 plus 1 over 6. So if I assume that the k case is true, that the k plus 1 case must follow. All the k plus 1 case is replacing all the n's with k plus 1. So the actual logistics of it, I don't know if it's actually important at all for you guys to be able to do it, because you can't really make a multiple choice question out of it. Really, they're just going to ask you to identify the 1k and k plus 1 cases for a given statement. That's all that they're going to do with it. So I don't know, to prove this algebraically takes a bit of a while. We don't quite have a bit of a while. We might do it at the end if we get extra. Okay, so stats, all the stats that you're doing in this course are going to be basically the measures of center and the measures of variation. So, measures of center are what you've been doing since like 7th grade. The mean, the median, and the mode. These are 3 different ways of, if you give me a set of numbers, I can tell you where the center is. And some of them suck for some purposes more than others. It's important to have all 3, because in some situations, mean will be great, and median will not be really what you want to report. In other ones, mean will be a terrible number, which will totally misrepresent your data. So remember that your mean of a set of data equals, add all the data points together and divide by the number of points. And it's great, it gives you what we call the average, but it's also kind of sucks because it is incredibly weak towards outliers. So if you have a class which is all clustered up around, let's say 84%, you've got an 83 and 84 and 85 and 84 and 83 and 86 and 87, and you get one jerk who gets like a 4%, if you take the average of that set of data, it's going to be like in the 60s or something, which is not a great representation of how that class did. That was an 80%, 84, 85% class and one moron, right? But it's being reported as if you've got a bunch of 60%ers in there. So the mean is incredibly influenceable. That's not the word.
Influential.
It can be influenced by, and there's a great word for that, but it's not happening right now. So, if you have outliers, it really messes up your mean, and you get a number which doesn't really reflect what most people are doing. So mean is great as long as either your outliers are evenly spaced, or as long as the data is pretty close, but if you have just a few random outliers, it'll totally screw up your mean. So this is vulnerable to outliers. So it's just like Pokemon. You pick the right Pokemon for the right battle. Right? If you're going into the water gym, you don't bring your electric type Pokemon. If you're going into a set of data with some weird outliers, you don't bring the mean to that fight. You bring the mean. The end. So median is, remember, you take the numbers, you write them in order, and if you have an odd number of terms, the median is the term which is directly in the middle. If you have an even number of terms, the median is the number which is the average of the 2 center numbers. So for instance, if I have 1, 3, 10, 11, 12, median is just the number in the middle, whereas if I have 1, 3, 10, 12, 14, 16, and even, then I take the average of the 2 middle guys, and that's my median. So what the median does is it's nice in that it really just gives me what's physically in the middle. But, so if outliers happen, it sort of ignores those. Right? I don't care if this could be 1, 3, 10, 12, 14, 49 billion, right? It's not going to care. It's just still going to give me a median of 11. So it's good for those situations where we want to kind of ignore the outliers, but it's terrible if I actually care about people on the outsides. So if I care about that 49 billion number, well, then I might not want to use the median. So the mode is just the number that shows up the most. You can have multiple modes. You cannot have multiple medians. You cannot have multiple means. But if you've got a set of data that has 5 6s and also 5 8s, then both 6 and 8 could be your mode. So as long as you've got the most. As long as both of those are modes. So what that brings us to, those are some ways of measuring the center, and they have their pluses and their minuses. You bring the right Pokemon to the right battle. But to sort of give a visual idea of what a set of data looks like, that's what our friend the box and whisker plot is for, which some of you might remember from back in the day as well. Box and whisker.
Oh yeah.
So let's say I've got this set of data. 1, 5, 6, 8, 12, 13, 16.
No, bro, no.
Yeah, race.
No, bro, no.
26. Okay, so there's my set of data. So what I'm going to do is first find the median. There he is. The median will divide me into 2 sets of information. I got this guy, and I got this guy. Find my median first, and then I want to find the median of the 2 sets I just broke things up into. So the median of this thing is going to be the average of 5 and 6, which is 5.5. That is what we call the first quartile or the lower quartile of this data. So the median of this part is 18, correct? That's the third quartile or upper quartile, depending on who you ask. Box and whisker plot, all you do is you take your low number and we start our box here at 5.5. $12 is our median, so if we, 1, 2, 3, 4, 5, 6, 8, 23, 24, 25, 26. Okay. So I'm trying to get an idea for this guy spaced out. So 5.5 is that, 18. So my box goes from my Q1, my first quartile, to Q3, my third quartile, and then I'm going to have a line in the center at the median, which is at 12. So what this guy looks like, here is sort of whiskery part. My other sort of whiskery part. And what it gives me an idea for is how are these numbers distributed? So I know my median is here, but I also know that in terms of outliers, my outliers are a lot worse on this side than on this side. Right, so I just got a tiny little bit outside the box here, but I got a huge amount outside the box over here. And I know that in terms of my what we call interquartile range, that I'm shifted a little to the right. I'm a little bit closer to 18 than I am to 5.5. So my median isn't right in the middle, it's shifted a little bit to the right. So that's what a box and whisker plot is that I have my box going from Q1 to Q3, a line for my median, and then my whiskers go out to the lowest number and the highest number. Now all of this stuff,
I knew it was
so all the median things rely on you ordering the information, right? So you put the lowest term first and then you just got to put them all in order. That gets a little bit tedious if, as you're going to have on your speedback, you've got like 30 or 40 points of data. Sometimes you'll want to do that, but sometimes it's a little bit tedious. So I recommend calculator methods, especially if you're only asked for one number about the set. Then going through the whole thing of creating the big ordering is a little bit silly when all you want is the mean or the median, if you just want one thing. But keep in mind, a note about calculators. Is that no matter what calculator you're using, let's say I wanted the median of a set of numbers, you go to your median button, that's either under catalog or it's under your stats. And what you need to do is insert a curly bracket. Curly bracket is your way of telling the calculator that you are giving it a set of numbers. If you don't put a curly bracket, it will yell at you. Then you close your curly brackets and you close the parenthesis. So remember your curly brackets. All these things, mode, median, mean, and what we're going to talk about next, standard deviation, those are all just buttons on your calculator. Curly brackets. Tell the calculator, here's a list. So it will do that, but it's a bit of work, but it's less work than probably putting them all in order, because it's really easy to leave things out when you try and physically write them out in order.
Oh, you need to do the curly bracket first.
Got to do the curly bracket first. So all that leaves then is talking about the standard deviation. Which is, it's not a measure of center, it's a measure of variation. In other words, what it measures is how closely packed am I around that mean value. The lower the standard deviation, the closer all of my data points are to the actual average. So if I have 84, 85, 85, 86, 87, that's going to have a really low standard deviation because all the points are really close to each other. They're really close to the mean. But if I have 3, 21, 51, 92, 246, those guys are pretty spread out. So that's going to have a really high standard deviation because there's a lot of spread. Now, standard deviation is actually sort of the beating heart of a lot of the analysis that you do in introductory statistics. It's the thing that tells you all sorts of stuff about the percentage of a population which you can expect to attain a certain score or to be a certain height or stuff like that. It's tremendously useful in your first level of analyzing a population. For us, all that we really care about is that you're able to calculate it. Calculating it by hand is a huge task, where you've got to calculate the mean, calculate the difference of the mean, square that, add them together, take the square root, divide by 1 less than the term. It's big. Luckily, you have a standard deviation button, so use that. That's what you're going to want to be doing on this particular test. So the actual calculation is more than you're going to want to deal with in this class. This is pre-calculus. If you go into calculus, it's something that you'll want to investigate a little bit closer. But for the purposes of this class, you're just going to want to look for your stdiv button. And use that. And that will calculate your standard deviation for you. So that's the idea. So you just need to be familiar with what those terms basically mean, and then how to if you're given a list, how to calculate those. And you're really looking at knowing how to use your calculator on that. That's sort of what they're expecting you to use. And if this were a full-fledged class in stats, well, then we do something more with it. But it isn't.